infrastructure team without really much investment. Now, I do think that there's, part of that ecosystem slide to end that I do wonder if in the future there will be an opportunity for this to be provided as more of a service where you're doing it on cloud right now, you do it on that can be a little bit more smoother, but I don't know of any service out there that makes that really easy right now. But I actually think you can do a lot of experimentation on very little money, and you shouldn't spend a huge amount of money building a supercomputer initially. Yeah. Oh, no, not laptop. Definitely desktop with some, the question was 100 million images, definitely desktop. And just the really good GPUs and people who know how to program them well. Get back there? Did you have any strategies, thank you, did you have any strategies for composing different results with composing different feature learning? Oh yeah, so the question is about composing different results learned by different things. So if you want to read more about this technique, this general area is often called model ensembling, ensemble like a group of musical instruments, where you might train models in a different way and allow them to collaborate to make a more intelligent decision together. And there's a whole set of literature on it. Ensembling is great. Almost all of the competitions that you look at, almost all of the time the winners use ensembling in some way. I have so many as well. If anyone has a real pressure, okay, last one right in the back there. Just hold on a sec for a second. So you mentioned ensembling as a way to compose different models. So that works great for doing competitions, but is that a commercially viable approach? That's a great question. So ensembling for commercially viable is commercially viable. And so one thing is that it creates technical debt. So if you have to run many models, it means your serving costs go up, it means software complexity goes up, your engineers need more engineers, you need smarter engineers. So that ends up being a trade-off about, okay, how big of a quality win, how much more complicated does it make my system? And sometimes that's a good trade, sometimes it's a bad trade. Okay, I'll be off the stage now. One set, and then a little bit later you'll also hear from Ian Sutter. uncorrupted input. And it turns out that actually does quite well on these adversarial examples. On these examples, when training adversarial examples. This is a little bit unusual because the adversarial examples never appear in the test data set. So by including the adversarial examples, we force the model to discover concepts that are closer to the true concept explaining how to classify data. In the future, there's a lot of ways to figure out how to encourage true understanding. Adversarial examples, training adversarial examples, and techniques, and discussion books every model. We're not learning how to figure out the underlying pattern in the discussion book and process things correctly. Some people think that the model has the potential to convert into adversarial examples. I've read the text of existing adversarial models, and they actually are not consistent with these adversarial examples, but it's possible that other adversarial models could be. Finally, I open these promising to train agents that can interact with the environment, and we can learn that the set of dynamics in the environment different from the structure of the if you look at the technical details of data work, the actual quantitative experiment has some more details about how you can predict exactly how adversarial examples will be formed, how they will be labeled. So I encourage you to look at these two publications from my team over the last year. Answer your question. So you look at adversarial examples, right? Comparison with other data optimization to see how very much like optimization. I like which one has the most marginal benefit. Yeah, I wanted to compare which one has the most marginal benefit. So I started with the state-of-the-art of specific tasks. And so the adversarial data aggregation is in addition to other things like you can drop out to augment the data by having different subsets. But in addition to like shifts of the image and then force the image like a different conclusion on it. Like I was saying, which one is the most beneficial one to do. Linear generation of adversarial examples and the way that they affect in addition to that. If you impose any kind of manifold individually to original on that manifold by direction on that manifold variable, you can also form adversarial examples by rotating the input or rotating different inputs in certain directions. And so in that case, normalization can prevent you from moving in a direction that a direct linear path that Euclidean space wants to move. So you can just do the sort of differentiation along the normalized manifold and rotate in that direction. And that will reliably confuse the network as well. Yeah, I tried a variety of things like that to see if they could convert resistance, and I haven't succeeded yet. And actually, even when coupled with adversarial training, they don't seem to make a lot of improvement. Yeah, essentially. It's important to update the set of adversarial examples on each mini-class rather than use the single case every time, because the set of adversarial examples is a function of the set of network weight. of course, the military risk. I signed this letter asking governments to take steps to avoid arms-based using AI for military weapons. Other than that, include in the short term, allies and to use these technologies, and I think it could potentially, right now, we think something that is creepy, but those mission systems sort of I think become more powerful because they must oftentimes becomes a little bit like if they were manipulating us, and there's like a political company and they think that as a part of people start thinking this is not okay. How this means manipulate people with political advertising. So there's a little bit of advertising, and I like it. I like that it's my mind, but actually there are other people and those billions of dollars. But when this becomes smarter, I think it becomes more, there's something that easily find opposite. As first, right now we're very good at finding systems, and we can tell if you're a British to have a British accuracy to say business here, and we need to do business with things that learn without having to take a 10 of the time. For example, if you're the cities of the world, so they have tracking the world, 10 or 20 for most of the time, so half that and it's really more intelligence very well, probably this also doesn't investigation because there's a lot of data out there that we can come with information which is industry and like the kind of questions people ask about systems or customer relations and customer service. They're probably less literary and more sort of historical fact-based. Alright, so I mentioned that we don't just want to understand place price output, so we also want to have systems that understand the world. And ideally we actually have systems that combine both of these worlds and can understand how they're related. So here we have a paper from 3 years ago that I published at Stanford, and we now also improved the research at Medline, where we essentially now send and images into the same vector space, and now we can look up one from the other. And instead of just showing that to you in theory, let me show you a live demo of this. So here we have the word bird, and as I type in bird, it basically looks at just the pixels of the images, and it's just going close to the image and the text side. And just on the pixels, it's now showing me images that are close to the vector representation of bird. Again, this is not just like Lewis bird, it looks at the text around the image, but it just looks at the pixels and looks at the word. So I type in bird, and once I change bird to bird, it doesn't just show me pictures of a single bird now, but it actually focuses on images where you show multiple birds. So I actually have some understanding of plurality. So now I can say bird water, and it actually will show me mostly pictures of birds on water, and not just some random kinds of words. So it has some idea of how you compose these words and the meaning, the physical meaning. You can also say bird, and then bird, and the images, and it is that for bird tree. And you can say horse, you can even say horse with full man, and it will actually find that.
毎度都営バスをご利用いただきましてありがとうございます。このバスは豊様北、小型、応援自立経営新宿駅西口に向かいます。次は富士見町都営住宅前、富士見町都営住宅前、北は大学小学校前でございます。お客様にお願いします。車内での通話が他のお客様のご迷惑となりますのでご遠慮いただきますようお願いします。また、歩行中の携帯電話の使用は危険ですのでやめましょう。次は富士見町都営住宅前でございます。次、止まります。扉が開くのでそのままでお待ちください。
system and they can go through all Instagram or Twitter images, try to find specific brands, and if you are familiar with review making, develop images for 38 different classes or so. The computer matrix still quite working very well. Or still very good performance. All right. With that, I want to conclude. Basically, it's to minimize errors and duplicate the art in AI and keep learning the way to do that, and then also make it more successful. Thanks a lot. Right now they don't share anything. They have different architectures. Those are different models, different trainings. They wanted to do the same test. So in this case, let's say train model A on the part of the data called T1 is actually 0%. Currently training will be on the piece of data on the T2 piece of data is actually 0% error. You can see that, of course, if we evaluate model A on the T2 piece of data, which it was not trained on, is actually essentially accuracy, that the test accuracy 2.4, or on the or model B trained on the tested on the T1 part of data actually also test accuracy. But here we have done the same figure on the previous slide. We generated negative examples for the model A, which gives 100% error. On the model A, we generated negative examples for model B, which gives 100% of error. And actually, exchange between model A and B, they actually contain some strange pattern, which is not recognized for us, but actually harms the model performance. We have several explanations for it. There are also some follow-ups on it. So one of the consequences of, let's say, of like living in the high dimensional state and making matrix multiplication over there is that if you have, for instance, 1,000 dimensions, if you move within every dimension like epsilon, actually after multiplication, you move essentially like 1,000 times epsilon. Even if every dimension is sort of it all has very small change, and like if you consider all of them together, they might sum up huge changes. Also another way of that, and that's essentially what I was explaining as the consequence what the reason of our another partial explanation is that maybe our linear operator they might be sort of unstable in the sense that maybe single eigenvalue dominate them and actually make them unstable. So I mean there is like many questions coming out of this in terms of how to potentially improve our model, or maybe it's harmful for our model. Someone would let's say prefer like a manually run the images that would follow all the fulfill all the models and so on. What are the like far reaching consequences of this? And also the question what should you do to really understand what the underlying computation? And I would say I don't know. Yeah, essentially. And in terms of conclusions, it's surprising that the single learning algorithm actually gives rise to very similar statistical properties of different models, even though they might have different architectures, they might rely on the different trainings, and they eventually they to some extent similar computation. As you can see, they in the same way fail on the negative examples. And the question is how we can, let's say, learn from it and make our models better. Thank you. And this is warranted big investments in building these kinds of systems for increasingly